Hey everyone, today I'm going to talk about this idea of dielectric breakdown. What that means is that the electric field strength between two charged objects reaches a maximum where the air becomes ionized and allows charges to move through the air. So the air is an okay insulator, but if the electric field strength grows to, you can see there, 3 megavolts per meter or 3 million newtons per coulomb, when that electric field strength has been reached, then the air becomes charged and charges are allowed to jump from high to low voltage. So you can see in the video here, we are discharging our Van de Graaff generator using the discharge wand. The picture in the slide here shows you how the Van de Graaff generator works. Again, the motor rolls and moves the rubber band next to the little comb down there. It pulls electrons from the cone, sends them up to the dome, and electrons jump onto the sphere. Since it's a metal sphere, the charges sit on the outside, and eventually the electric field strength grows so strong that the charges jump, like you're seeing here in the video. The largest bolt we were able to create in class is around 17 centimeters long. So using that information, we should be able to figure out what the voltage of our generator is and the surface charge density of the dome. Also in that picture down there, you can see someone is operating a giant Van de Graaff generator, and they're actually sitting in that metal Faraday cage down there. So bolts are shooting down, people are watching them have these lightning bolts strike the cage, and the operator inside is perfectly fine. Like we said in the video, the Van de Graaff generator was charged to a very large amount. Let's say that the Van de Graaff generator was positively charged, just to make the numbers a little bit easier. And the charges jumped from the sphere over to the grounding wire. The grounding wire is at 0 voltage, 0 potential for the ground. If the electric field strength grows, we said, to that 3 million volts per meter, then the charges are allowed to jump through the air. So voltage is equal to electric field dotted with a displacement. The displacement was the 17 centimeters through the air, and we know the maximum electric field strength is 3 million volts per meter or newtons per coulomb, whichever one you choose. So when you do that, you end up getting a potential of our Van de Graaff generator of around 500,000 volts. So that's a pretty high potential, and you think that that would really just knock someone out. But again, it's not the voltage that gets you, it's something we'll talk about a little bit later. 500,000 volts jumping through the air, discharging all the charge from the Van de Graaff generator to the ground. But the generator has a motor in it, so it continuously pumps charges back up there, which allows it to build up more charge and discharge again and again and again. So with that known, we want to figure out, well, what is the surface charge density on our generator? Well, we could surround the generator with a Gaussian sphere, and we know that we could find the electric field strength. The electric field would show us that we're dealing with a point charge. So dealing with dV is negative E dot dr. We could solve for the potential. I'll let you do that, which gives us a potential of kq over r. We know the voltage on the sphere. We know the size of the sphere. I measured the sphere and it was a 32 centimeter diameter. So our r value is going to be half of that, 16. And we know the Coulomb constant. So if you want to solve first for the charge, that's easy. You can rearrange this and you should get around about 8.8 microcoulombs of charge, which is a decent amount of charge to put on that Van de Graaff generator. But the question wasn't just about the charge, it wanted the charge density. So that is charge over the area, so we know that. And since it's a sphere, we know our area is 4 pi r squared. Working through your math, you should get around 27.6 microcoulombs per square meter. Looking at all the fun pictures of lightning or this video of a plane getting struck, we know that when the air reaches a certain amount of electric field strength, the air becomes ionized and charges will go from high to low potential. So we've seen many people that like to try to capture the discharge of these clouds from the ground to earth or earth to the clouds. So our last example here is the hollow spherical shell, so with charge inside. This is similar to what we did earlier when we had a shell and we had a positive or negative charge inside, and we said, how does the outer shell react? Well, the first thing we can say is that if this charge in the middle is positive, we know that QA is the charge on the inner shell and negative Q is going to come in to meet it. If the shell was neutral, that means that it left behind all its protons on the outside and we have a positive charge out here. Overall, the hollow spherical shell is still neutrally charged, but charges have separated and redistributed themselves. Find the voltage or the electric potential as we move from infinitely far away all the way into the center. Let's start with our voltage when our radius is beyond the outer shell, so we're far, far away. Well, if we want to know what our voltage is, we could have the voltage from each of the charged surfaces. Since they're all spheres, we can use kq over r. So there's how we can find our potentials. Since we can see each of those rings as point charges, they're kq over r. qc is the charge at the center, qa is the charge on the inner ring, and qb is the charge on the outer ring. Well, since they're all the same charge, that positive in the middle induced negative to come in and left positive outside, there's no difference in the amount, we would have all these kq over r's actually be very close to the same. So this can cancel with that. Voltage way out beyond radius b would just be kq over r, which is what we expect. So when I go from infinity towards that shell, it's going to fight the field and I'm going to increase my voltage. Now let's go to the next scenario. So now, what's our voltage when our radius is in between A and B? So what that means is back in this location, what happens when our charge gets right here? Well, the first thing you want to do is talk about what electric field you'd feel at that point. The electric field inside metals we know is 0. So with no electric field in there, again, people want to say that there is no voltage. But that's not the case. We took all that energy to get you to the surface of B. So that means that inside the metal, our voltage is constant at KQB. As soon as we get inside the metal, we don't have to fight anymore. We've hit a plateau. We're good to go. What about when we get even closer to that central charge? Now we're inside the shell. Once we get inside the shell, we see that there's another charge, which means there's another hill we have to fight, and so we have a new potential that we can gain. So when we are at this location, getting closer and closer to that central charge, our total voltage, again, we can see as point charges, and we'll do K, charge at the center, over R, because we're just an R distance away now, but we've already passed through shell A and shell B, the inner shell and the outer shell. So we're going to have to subtract KQA over radius A, because the surface of any conductor is an equipotential surface, and we're going to have to add that to KQB all over B. And in this case, yes, the charges may be the same, but the distances are all different. So unfortunately, this is the answer for your voltage as you head closer and closer to the center. So that's why we get something like this. When you try to approach that sphere with a test charge from infinitely away, and you walk towards radius B, you're walking up that hill, you're fighting the field, and you're gaining potential energy. Once you get inside, the potential's nice and flat, the potential's constant at the surface of B. There's no electric field inside, so we get a constant voltage. But as soon as you try to go even closer, you can see it's going to jump up even more. It's going to be harder and harder to fight and gain energy as we get closer to that central charge. So the voltages are increasing when you fight the field, and they stay constant when there is no field to fight. Again, to prove that there are fields inside the shell and outside the shell, we'll do 3 quick Gaussian surfaces. Gaussian surface 1, I've wrapped up the central charge. There's charge enclosed. I know that I must have an electric field due to a point charge. Gaussian surface 2, I'm going to wrap up the negative as well as that inner positive. The total net charge there is 0, so the net flux must be 0. And when the net flux equals 0, there's no electric field. How about location 3? Gaussian surface 3 is way out here. You can see that my total flux is due to a positive Q, a negative Q, and a positive Q. Positive and negative will cancel out and just leave me a 1Q. So there is electric field outside, so I fight the field outside the shell and inside the shell, but not through the metal. So we've talked a lot about electric potential, voltage, electrical discharges like lightning. So I've left you a couple links here, like this Lord Kelvin's thunderstorm, or what is actually in a flame. We said flames were plasmas. So click on the links and see what happens when you put a flame in a large electric field. And also Destin talking about lightning and where the sound comes from when you get these big electrical discharges. So enjoy, and we'll see you next time.